Okay, so now that we've studied injective and surjective and bijective functions, we want to see how this is related to the cardinality of sets. So first of all, I just want to play around with the idea a little bit before I define something. And so first of all, we want to notice like if A is equal to the set 1, 2, 3, and B, I'm just going to kind of be silly here and make it the set which has a circle, a triangle, and a square in it, then we know these are the same size because they both have 3 elements, right? But that's because they're finite sets. We can just count the number of elements. And so now I want to be able to talk about infinite sets having the same cardinality. And so I don't want to count because if I count an infinite set, well, first of all, I'll never be able to count all the elements anyway, but I expect to get infinite if I tried even if you can make sense of that. So I need something else when it comes to infinite sets. So the idea is, so I guess I don't want this if here, but we can consider A and B, which we can define a bijection F from A to B. And remember, in a picture, the bijection where we have A over here, which has 1, 2, and 3, and we have B over here, which has a circle, a triangle. Well, maybe I should get rid of these little dots in this picture, actually. So we have 1, 2, and 3. We have a circle, triangle, and a square. And of course, the bijection, it could send things to various different ways, but the simplest way to draw it is 1 gets sent to the circle, 2 gets sent to the triangle, 3 gets sent to the square. And so this bijection is what we call a one-to-one correspondence between the set on the domain and the codomain. So bijection is the right definition to make sure that every value in the domain is sent to a unique value in the codomain, and also every value in the codomain is hit by a unique value. So it gives a one-to-one correspondence, or another way, what I was saying is it's a way of pairing off every element domain with a special buddy in the codomain. And since they get paired off in a one-to-one correspondence, everybody in the domain has a buddy in the codomain, we say that they have the same size. Okay, so I'm going to make that definition here in a second, but in the finite case, it's kind of clear. It's not interesting. It's like, sure, you can do this in the finite case, but in the finite case, you just count the domain and the codomain, and you get the same answer. So this is going to become interesting though when we start looking at infinite sets. That's where this is interesting. So, but let me make the definition first. So, definition. We say that two sets A and B have the same cardinality. And it's also helpful to know what the notation is. So denoted, we use absolute values. May not like that because we use absolute values for other things, but it shouldn't be confusing because you're taking the absolute value of a set. You're clearly not taking the absolute value of a real number. So we say that they have the same cardinalities, meaning the absolute value of A is equal to absolute value of B, where absolute value represents cardinality. If there exists a bijection, which is a function f from A to B. So if there is any bijection, we don't need a bunch of them, we just need one, right? As soon as there's one bijection, we say that A and B have the same cardinality. Same. Okay, so then let me just make one more definition before we move on here, which is to say we give a special name when you're the same cardinality as the natural number. So we say that a set is set, I need to give it a name. Set A is countable if the cardinality of A is finite, or if, so if it's an infinite set, or if the cardinality of A is equal to the cardinality of the natural numbers. So if it's a finite set, we call it countable. And if it's an infinite set and has the same size as the natural numbers, then we also call it countable. And furthermore, otherwise, A is uncountable. Okay, so we need to see examples now of infinite sets, because the finite sets, again, are not interesting at this point. We need to see examples of infinite sets, which are countably infinite and also uncountably infinite, right? So we need to see examples of both of these things to start to get a sense for what's going on here. Let's start out with a very simple example, maybe a little bit boring, but it's good to start out with a simple example. So we're going to show, first of all, that the natural numbers have the same size as the set of natural numbers starting at 2. So first of all, if you're not familiar with this, this is a little bit interesting because it feels like you got rid of something from the natural numbers. So it should have a smaller size. Certainly with finite sets, if you just take the numbers 1 through 7 and then get rid of 1, it's going to have a smaller size, right? But infinite sets are different. So um, in this case, we're going to show that they are the same size, even though I got rid of one number, right? I got rid of 1, but they're still the same size. So the proof is to exhibit a bijection, right? So proof. To prove the claim, we will show that f, so we're going to pick a function from the natural numbers to the set of natural numbers excluding 1 given by f of n equals m plus 1 is a bijection. Okay, and according to the definition, if that's a bijection, then they have the same size, right? I can pair off everybody in the domain with somebody in the codomain so that there's no duplicates, and so they have the same size. All right, so let's see how to do this. So it's a very straightforward proof compared to some of the other bijection proofs we've done in the past, but let's just do the details here. So to show f is surjective, let n be some number in the natural numbers excluding 1, and notice that if you plug in f of n minus 1, you'll get n minus 1 plus 1, which is equal to n, where n minus 1 is a natural number. So that's it, right? So I take, if you want to map onto n, which is in the numbers other than 1, then you just consider n minus 1. And since n minus 1 is a natural number, this works, right? So it is surjective. Now to show f is injective, consider n and m in the natural numbers so that f of n equals f of m, which implies m plus 1 equals m plus 1 for n equals m. Okay, so hence F is a bijection. And the two sets have the same cardinality. Great. All right, so this is our first example of doing this all rigorously as well. So yeah, these have the same size. So if you can get rid of just one number from the naturals, you still have two sets which are the same size, which is, again, is only, this kind of thing happens with infinite sets. It never happened with the finite sets. Let's look at one more example where we do this all like very explicitly using bijections. And so the next example is to show that the size of the naturals is equal to the size of 2 times the naturals, where I just have to define what 2 times the naturals are, just in case you've never seen that shorthand. So that's like the even naturals, right? 2 times 2, 4, 6, 8, 10, so on and so forth. Okay, now I'm getting rid of, it feels like I'm getting rid of half of the natural numbers. So you'd think that they're definitely not the same size, but again, they're going to be the same size. At least that's what the example says. So let's try to prove this. So to show that the size of n is equal to the size of 2 times n, we will show that. So f from the naturals to 2 times the naturals given by f of n equals 2 times n is a bijection. Again, if you can show that there's a bijection, then that's what it means for them to be the same size, right? So let's just check this carefully. It's easier than some of the other bijection examples we've done, so shouldn't be too bad. So let's see. Let's start with surjective. So to show that f is surjective, okay, so consider some number in 2 times the naturals, and that means that n is equal to 2 times k for some k in the naturals, right? That's what it means to be in 2 times the naturals. You're some even number. Any even number can be written as 2 times the natural number. That's how we defined even numbers. But this kind of like falls into our lap, right? So f of k is equal to 2 times k. That's how the function is defined, which is equal to n. And we're done, right? So that's easy. And then to show that f is injective, consider an n comma m in the naturals so that f of n equals f of m. This implies that 2 times n equals 2 times m, or n equals m. Hence, f is a bijection and n and 2n have the same cardinality. Very good. So now we've shown rigorously with the proof that these are the same size, right? And so that means 2 times the naturals is also countable. And it's a bit surprising, again, if you're not used to this, because it feels like the even integers, or sorry, the even naturals are like half of the naturals. So you might think that they're half the size, but yet they're not, right? It's okay. They're the same size. And so infinite sets are bizarre in this way. And you have to learn sort of new intuition for cardinality of infinite sets, because it's much different than what you're used to for cardinality of finite sets. So we'll look at many more examples of this kind of thing going forward. But here we gave the rigorous definition of what it means for two sets to have the same cardinality. There must be a bijection between them. And we've done two simple examples showing bijections to show that sets are the same cardinality. And in the future, I'm going to teach you a little bit of a trick to show that sets have the same size of the naturals by just listing out the elements, which is a way of sort of demonstrating a bijection without having to write out the function in this particular way that we've been doing